Let's look at some application problems using exponential functions. We call that modeling with exponential functions. You've already seen a few application problems that involve exponential functions where you were given the input, you had to find the output, or you were given the output, you had to find the input. But in all of those examples, you were given the formula, you were given the function. The exception was when we had compound interest, then you could just use the formula. And remember that for compound interest, we looked at the example of a continuous compound. And the formula for that was the amount of money you have after t years is how much you started out with times e to the rt. Well, we're going to do something similar for other modeling problems where instead of money, you're talking about, let's say, the population of something or the amount of something, number of bacteria, number of frogs, some other situation other than money. And so instead of a equals p e to the rt, we are going to use n of t equals, and then instead of p, the starting amount, we'll just call it n sub 0, how much you started out with, e to the rt. So t is some kind of time measurement. It could be measured in this case in days, minutes, years. It depends on the problem. And then for that function, r is called the relative growth rate. Another way of writing exponential functions that we have been working with before was we wrote f of x equals a times b to the x. So we didn't use e at all in some of our examples. And we're going to do the same thing in this section. Look at application problems where, again, instead of a, that y-intercept, we'll call it n sub 0, the initial amount, times b to the t. An important special case of this is when we know what we call the doubling time for exponential growth models. So doubling time is exactly what you might guess it means. It's the time it takes for the amount of something to double. So if you call the doubling time a, then you can use this formula, this function, n, the amount after time t, is equal to the initial amount times 2 to the power t over a. And you can show this by just using the formula and then saying if after a units of time the amount becomes double what it was, then what is the base? And you can show that the base is 2 to the 1 over a, and that's how we get this formula. Sometimes we have exponential, so this is for exponential growth models. If you have exponential decay, then the important number, which is the counterpart to that doubling time, is what we call the half-life. And so if the half-life is h, let's say, half-life is the time it takes for the amount of something to become half of what it was. So if it started here at time 0, let's say, and then half of that is about over here, how long did that take for the amount to become half of what we started out with? In that case, you can use the formula n equals the starting amount n sub 0, 1/2 to the power t over h. So depending on the situation, you could use one of these formulas. When you write an exponential function to model growth or decay, if you use either one of these, you get different looking functions, but they will give you the exact same answers. You have a different number for b, and then here you have e to some r, but really that e to the r is the same as that b. So you have to follow the instructions and see what you're asked to do. Are you asked to work with that e to the RT type of function or b to the t? Let's look at some examples. Suppose a rumor is spreading at SBCC that classes will be free next semester. Assume that 5 people have heard the rumor as of today, and that the total number of people who have heard it doubles every 3 days. So that's an important piece of information. Doubles every 3 days means that the doubling time, which we called A, is equal to 3. Let f of t be the total number of people who have heard the rumor at t days since today. So f of t, instead of n of t up here, we're calling it f of t. Again, always follow the instructions in the problem. What your function should be called equals n sub 0. So the starting number, how many heard it on day 0? 5 people, times 2 to the power t over a. See, you can check this. At time 0, 2 to the 0 is 1. 5 people have heard it. After 3 days, if you plug in 3 for t here, you get 3 over 3 is 1. Then 2 to the first power is 2. 5 times 2 is 10. See, it doubled after 3 days. So this function represents, models this situation. Then the rest of it, once you have the function, it should be easy. How many people will have heard the rumor 7 days from now? That means you just have to calculate f of 7. Plug in 7 for t and put this in your calculator, which gives us approximately 25 people. Next question, how many people will have heard the rumor 30 days from now? That's the same type of question. They're giving you the days. And because the doubling time was given in days, then all the measurements of t are going to be in days. So yes, for 30 days, I would plug in 30. If they had set 1 month and it's a 30-day month, I would still have to put 30 because the measurement has to be in days. 5 times 2 to the power 30 over 3, and that equals 5 times 2 to the 10, or you can just put it just like that in the calculator, which is 5,120 people. Now in the next question, they don't give you the input, they give you the output. They say how many days until 25,000 people have heard the rumor. So for that, we would have to use that same function, but now put 25,000 for the output for f of t, and then solve for t. So I will write 25,000 on the left-hand side of this equation. Now t is up there in the exponent, what we have to solve for. So this is an exponential equation. I can't make bases match the way this is. I do have to take logs eventually, but first I have to get rid of that 5. You have to get that exponential all by itself first. So we divide both sides by 5, and we get 5,000 equals 2 to the power t over 3. And now that the exponential is by itself, I will take the ln of both sides, and that wraps that t over 3 to the side. So we get ln of 5,000 equals t over 3 times ln of 2. T is the variable here. It's a linear equation. I just have to get rid of that ln of 2, and I have to get rid of that 3. I'm going to do both of those things at once. I will multiply both sides of the equation by 3. Remember, always clear denominator. And that gets rid of that 3, and then I'll divide both sides by ln of 2. Let's put this in the calculator and see what we get. I get approximately 36.86, which I will round to its days, so about 37 days. So we use the information to write the function, and then in a couple of parts, the input was given, we plugged it in to get the output. In the last part, the output was given, we plugged it in, and then solved for that input. So keep in mind, again, the different types of functions that you could use. There's that n of t equals the initial amount times e to the rt, which looks just like continuous compound formula. Or you could have n of t equals n sub 0 b to the t. Or you might have the special case of this one where you have the doubling time, and so it's 2 to the power t divided by the doubling time. Or you might have the half-life t, so 1/2 to the power t over h. So depending on the problem, you might have to use one of these formulas, and sometimes you have a choice of more than one. Next problem says the population of a certain species of fish has a relative growth rate of 1.2% per year. So that right there is telling me that I should use this version, and that R is equal to 0.012. Relative growth rate is just like interest rate in a continuous compound problem. It is estimated that the population in 2015 was 6 million. Find an exponential model for the fish population in millions t years after 2015. So that means that 2015 corresponds to t equals 0. So if I know that the population was 6 million in 2015, that means I can work with this ordered pair. When t was 0, the population was 6 million. It's the y-intercept, or whatever you want to call the function, the n-intercept. It's n sub 0. That's what that's telling me. So I have r, I have n sub 0. I can just plug them in here, and I have my function. N of t equals the initial amount, which is 6, e to the 0.012 times t. That gives us the fish population t years after 2015. So what's the fish population in the year 2020? Well, if we're counting from 2015, 2020 corresponds to t equals whatever 2020 minus 2015 is, which is 5. So all you have to do for this part is just plug in 5 for t. And just plug all of that into your calculator. Let's see what we get. Looks like it's approximately 6.371 million, because we are measuring this in millions. We plugged in 6 million for the initial number, about 6.371 million fish. The next question asks, in what year will the fish population be 10 million? So now they're not giving us the input, they're giving us the output. So I'll plug it in for n of t, and then we have to solve this equation. It is an exponential equation because t is in the exponent. I will have to isolate that exponential factor. So I'll have to get rid of that 6. We can do that by dividing both sides by 6. 10 over 6 simplifies to 5/3, but I wouldn't write a decimal approximation. Remember, we never want to round in the middle of a problem. So 5 over 3 equals e to the 0.012 t. And now to bring that t down, we'll just take the ln of both sides. And the nice thing about having that e is that ln of e, basically they cancel each other out, just leaves us with that 0.012 t. I'm going to move over here. we get 5/3 equals, ln of 5/3 equals 0.012t. To get t by itself, we'll just divide both sides by 0.012. And put this in the calculator to get an approximation. Looks like we get about 42.6, and the units for the t were years. Oops, but I really shouldn't box that up. Always answer the question that you were asked. In this case, it's in what year? Well, so if year 0 was 2015, then I have to add that 42.6 to 2015, which is 2057.6. So you can interpret this two ways. It's still in the middle of 2057 when it's 0.6, so you can say in 2057, or you can round up and say, well, you know, it doesn't happen at the beginning of 2057, but by the end of 2057, so you can also say by 2058. I would accept either answer. Let's look at an exponential decay example. A scientist wants to estimate the age of a piece of wood. The half-life of carbon-14 is 5,730 years. So half-life, in my formula, I just call it H, is equal to 5730. So if we are going to use that formula, n of t equals n sub 0, 1/2 to the t over h, then I'll know what to plug in for that h. Let f of t represent the percent of carbon-14 that remains in the wood at t years after the wood dies. So every living thing has carbon-14 in it. Once it dies, the carbon-14 starts to decay. It starts with 100% of the amount of carbon-14 present. After 5,730 years, half of it is gone and half of it remains. So the function that gives you f, in this case, again, they want us to call it f of t instead of n of t, is the initial amount, which is the 100%. In this example, in other examples, you might talk about, oh, there's let's say caffeine in your bloodstream that's going to decay, that goes down over time. Or there's alcohol in your blood that goes down over time. So then instead of 100%, you might have there's this many milligrams or this many whatever. So you always put that initial amount, whatever it is, right here. In this case, it's 100%, times 1/2 to the power t over the half-life, which is 5,730 years. So this function gives us the amount of carbon-14 that remains in the wood at t years after the wood dies. Use the function f and set up and solve an equation to estimate the age of the wood if 20% of carbon-14 remains. So that 20% is not a number I'm going to plug in for t, it's a number we'll plug in for f of t. Since we put the 100% here as 100, the 20% on the left-hand side will be put in as 20, and we have to solve this equation. So it's an exponential equation because there's a t in the exponent. I have to isolate that exponential factor. So I have to get rid of that 100. We'll divide both sides by 100. 20 divided by 100 gives us 0.2 equals 1/2 to the power t over 5730. Then, now that the exponential is by itself, I want to bring down the power. So we take the ln of both sides, and that brings this exponent down to the side. Bring the cat down from the tree. And then we get ln of 0.2 on the left. t over 5730, ln of 1/2 on the right. To get t by itself, this is now just a linear equation. We want to multiply by the denominator, multiply both sides by 5730, and then divide both sides by that ln of 1/2. These are just numbers. They look funny, but they are just constants. So we get 5730 times ln of 0.2 on top and ln of 1/2, or ln of 0.5, you can also write on the bottom. When you put this in the calculator, you get approximately 13,000. And I would just round to the nearest year. I mean, we're talking about thousands of years. We don't need a fraction of a year. So about 13,305 years. Before I do the next application problem, I want to look at a purely algebraic problem. You don't have any quantities represented by these numbers here. So we'll just set up the equations. It says find an equation for the exponential curve that goes through these 2 points. Now you've done this before for lines. You have 2 points, you find the slope, you have the y-intercept, you write the equation of the line. Well, we're not trying to come up with a line. We're trying to come up with an exponential curve. So for the exponential curve, I want to get this form of my function, a times b to the x. Well, this first point over here is a very important point because it has 0 as its x-coordinate, which means it's the y-intercept. And that means that that y value of that point, the y-coordinate, is just a. So I already know one of my parameters, one of the constants I have to find for this function. It's 97.2. So the other number I have to find is this b. How do I find that? I know that when x is 4, y is 17.1. So I will just plug those numbers in. 17.1 equals 97.2 b to the power 4. How do we solve this equation? You want to get that b to the 4 by itself first, so we'll divide both sides by 97.2. And do not round that, just write down exactly what you see. Now, to get rid of that 4th power, we raise both sides by the 1/4 power. You can also write it as 4th root. Now, generally speaking, again, just if I was just trying to solve this equation, I would have to put a plus or minus. That's what you do whenever you do an even root to both sides of the equation. But we're trying to find the base of an exponential function, and that can never be negative. So I am not going to put a plus or minus there. It's just the positive. So b is this number, the exact value. You can write it as 1/4 power. I'll just write it like this too, just so you can see both versions either way. 17.1 over 97.2. When you put this in your calculator, you get approximately, I'll write it to 4 decimal places, 0.6476. So we have a, we have b, we can write our function. The answer is, they said find an equation for the exponential curve. This is the equation, f of x equals 97.2, it is approximately, times 0.6476 to the power x. So why did I do this problem? It relates to the next application problem. A bacterial culture begins with a population of 57. That's a key word right there, begins. That's the initial amount. That tells me the quote-unquote the y-intercept, or the n sub 0 if you're trying to write the function like that. After 2 hours, there are 155. Assuming exponential growth, write a function that gives the population at t hours after the original count. So I want to write this information as ordered pairs. At time 0, the population is 57. 2 hours later, the population is 155. They do not specify here if you have to write the function in the form n equals n sub 0 b to the t, or n equals n sub 0 e to the rt. I am going to do it the same way, and I'll show you a problem you're going to see in your homework in WebAssign. And it asks, I'll just show you when we get there. It asks for this form, but even if you put this form in, it does not mark you off wrong. So either way is correct. We know that at time 0, the population was 57, so I know that that's my n sub 0. And I know that after 2 hours, the population is 155. So this is just like the problem up here. We're plugging in the numbers to get the value of b after 2 hours. So we will divide both sides by 57. And we get b squared equals 155 over 57. Then we square root both sides, which again, normally that means I would have to put a plus or minus. But because the base of an exponential cannot be negative, I won't do that. It's just the positive. So that gives us b is approximately whatever that square root is, about 1.649. So I'm going to move over here because I want to reserve the spot here for the other type of function. Then our function is n equals n sub 0, which is 57, times 1.649 to the power t. You could have also gotten the answer in this form if you put, again, 57 for n sub 0 and 155 for n. And then we don't know what r is. E is a constant, and t is 2. So I'll just write it as 2r. Then you would divide both sides by 57 again. Then you would now take the ln of both sides. And then you would divide by 2 to get r. And I'm not going to put this in the calculator. You get some value of r. You would plug it in here, and that would be your function. I personally like this one better when you have a problem like this where you just have two ordered pairs, basically, just like when you're trying to find the equation of a line, but now it's an exponential function. Just plug in your intercept in for the initial value and then solve for b. So this next problem is part of one of the homework problems you'll see online. It says the population of California was this much in 1990 and this much in 2000. Assume that the population grows exponentially. They want you to find the function that models the population. So I prefer this form of it, but I think they're looking for this form of it because they say round your R value to 6 decimal places. Well, I tried it and I put the equation in this form and it accepted it. So you can also do it this way and then put B, write B to 6 decimal places. Or you can do it this way and then write your R to 6 decimal places. But I recommend to start this problem to write the information as ordered pairs. If t is years after 1990, then 1990 is the year 0. In that year, the population was 29.76. And then in the year 2000, which is 10 years after 1990, the population was 33.87. And you're trying to write an exponential function. So it's going to look something like NFT equals the initial, which is 29.76. The rest of it you have to find. It's either going to be some number to the t, or it's going to be 29.76 e to the some number times t. No matter which form you pick, I would round the number that you're finding here to 6 decimal places as directed.